Thank you very much for inviting me. Maybe this will be the outlier talk, we'll see. Uh, it's also very nice to have my name pronounced correctly. It's not often during the conferences. Okay, so let's move on. So this will be, I will need to introduce definitely some basics of two-dimensional infrared spectroscopy. I think I'm the only person talking about this at the conference. Then some motivation, which I think makes this very interesting to work experimentally towards gas phase two-dimensional infrared spectroscopy. Some experiments that I have done during my postdoc on the way to get there. So not 2D IR, but ultra-fast and with cavities and frequency comps. And how exactly we want to do this cavity-enhanced 2D IR spectroscopy. And I crossed out this part because almost certainly I won't have time to talk about this. But I have the slides. And it's also quite interesting. So I think a lot of people coming from atomic physics, like when they think about several different lasers interacting with some atomic or molecular system, then usually we consider this kind of setup where we have some atomic levels. So this is an example scheme for electromagnetically induced transparency, and basically we have a continuous wave laser fields. So we have some new steady state of light and matter, and we can describe new properties of this state. But then we can consider like the same the same matter state, but now we have continuous wave, now we have pulsed lasers. So what this means? Well, this means that I have one interaction between, let's say, this state and this state, and I have free induction decay of this population, of this coherence that I have created between two quantum states. And then I come in with another pulse, and what is important is, so I have some oscillations that I induced, and I also have oscillations of my pulse. And clearly, the overall final signal that I will measure will depend on the relative phase of the coherence I created in the matter and the phase of the pulses that come in. So I will be able to see in quantum interference by using different pulses which are phase coherent. And this way we can, so this is essentially I can describe the same kind of matter system, but the approach experimentally is quite different. And what is important is that here I can kind of think about it in the way that I have interaction, I have this excitation and then this excitation, and then I flip the time ordering of the interactions and to account for all the possible ways the system can be excited. And then if we take some simple example, I have three pulses. So usually we want to describe it with density matrices. So we have first interaction, we create off-diagonal coherence, we let it evolve for some time, and then this phase is fixed by the frequency of interaction, by the frequency of the difference between the two states and how much time I waited between these two pulses. And I have another pulse where I drop down to population, and then with the third pulse I create this off-diagonal element again. I wait for some time and I have my final third order nonlinear signal. And obviously in real systems we have in real atoms, molecules, or solid state samples. I can have many different pathways of interaction. I can couple many different states. And the way we like to describe this kind of different ways to excite quantum systems is by these double-sided Feynman diagrams, which essentially allow us to track the bra side and the cat side of our system independently, and then based on reading out what happened, describe some single component of the third order nonlinear signal. So what's also important experimentally is that in the end, since we have three different beams, usually three different lasers, we have phase matching condition. So in the end, our signal will be emitted in some specific direction. And you can see that depending on the kind of pathway we consider, we will also have it emitted in different directions. So this allows us also to decompose the whole experimentally the many different ways the system can interact by looking at different directions. And I said that this is phase coherent interaction, at least ideally this is what we want. Then we can also manipulate what we measure by looking at different phases of the simulated signal, because we also add them differently depending on how exactly the interaction goes. This is an important point. So in the end, usually people use this kind of techniques, two-dimensional infrared spectroscopy. Well, it's infrared, so we study vibrational excitations, fundamental modes of vibrational excitations. And since this is nonlinear spectroscopy, we have free pulses. So that means that from the get-go, our signal will probably be 100 times lower than the best, fundamentally than the best linear spectroscopy. So we need samples that have large cross sections that also that in general absorb strongly. So usually this kind of measurements are done in liquid phase. Usually large systems where, for example, here this is an example where we have this large molecule. We excite asymmetric stretch and we excite symmetric stretch, and by Fourier transforming our signal along the two delay times, we can obtain these two-dimensional correlation maps. So what this means is that on the diagonal, essentially, I have mostly the same information as for linear spectroscopy, but when I get a signal on the anti-diagonal, especially as a function of the waiting time, that means that if I excite this mode and I wait a little bit, then some of this energy flows to the other mode. So there is some kind of coupling in my system that I can track. So as in the morning, Gerhard Meyer said that when we do thermionic ionization, so we excite some vibrational modes, we give a lot of energy in the vibrational mode, and somehow this energy flows such that the system ionizes. So essentially, 2D IR spectroscopy allows you to measure what exactly is going on after you put some energy into the vibrational mode. So it's also, it's useful if you have system which is complicated enough that vibrational dynamics are not trivial. So if you're interested in diatomic molecules, then it's probably not very useful. But if you're interested in larger molecules, then it can reveal very interesting chemistry and physics. So what I want to do is I want to use this for gas phase samples. But my problem is that, well, most of the technique development was done for samples with broad features, so low spectral resolution, and most of the techniques are low sensitivity. And this is an example also why it would be interesting to go to gas phase. So here we have 2D IR spectroscopy of water. So we can see here, well, maybe this is not clear from the back rows, but here we have the frequency of initial excitation. So this is between, this is in the mid-infrared. We excite asymmetric and symmetric stretching modes. And then we see that basically the energy goes everywhere. Because after we wait some time and then we come in with another pulse, you can see that the response stretches from 1600 to 3600 inverse centimeters. So that's a huge part of infrared spectrum. And why it happens? Well, because we are looking in the liquid phase. And in the liquid phase, we have many different clusters of many different sizes of water. We don't have isolated water. And essentially, we introduce some energy in this symmetric or asymmetric stretch, and then it goes everywhere. It strongly couples to bending modes. It also couples to the modes of the whole cluster. It was also shown by that some of the excitation basically become delocalized and are shared by the whole cluster. And definitely, if you wanted to very precisely understand what is going on in this system, you would like to see what happens in dimers, in trimers, in tetramers, pentamers, hexamers, but separately, not all at the same time. So people have been doing spectroscopy in the gas phase. So Saikalis group in 1998, this is CRDS spectrum of water, of small water clusters. You can see that you can spectrally resolve them if they are in the gas phase and they are cold. But this is CRDS linear spectroscopy. So that means that the signal was weak. And as I said, with ultrafast spectroscopy, it's going to be even worse. And so nobody has done 2D IR of water gas phase yet. And recently also, McKellar and Moazen Ahmadi's group have also been doing measurements of dimers. And so to do this kind of thing in 2D IR, I need to do ultrafast measurements which are ultra sensitive at the same time. So it's quite difficult. And also another motivation for this is to solve some problems in molecular line shape theory that have been commonly solved or studied with linear spectroscopy. So why we are interested in general in molecular line shape theory? Because it's important for interpreting spectra from astronomical observations. It's important for interpreting spectra from atmospheric observations. We want to know very precisely the concentrations and pressure and temperature of what we measure. And so this is a very brief introduction what's going on with gas phase molecules when we excite them and when they collide with gases. So obviously we have, this is a simple example. We have the atomic molecule, it has some rotational state, it moves, and then we excite it. So as I showed before, we create some kind of coherence. It has some dephasing, and there is some dephasing and damping of this coherence given by the gamma. The sign is wrong here, obviously, but here it's correct. Given by the gamma parameter. So from this we will simply get Lorentzian profile. But then we have some distribution of velocities of the molecule. So we would have speed-dependent Lorentzian profile. This is quite easy. On the other hand, we have inhomogeneous broadening. So we have so now we ignore homogeneous broadening. We have distribution of velocities. So we will have, so due to Doppler shift, we will have Doppler broadening. So we have Gaussian profile. But then actually what we're interested in is not just velocity, but the path it takes. And if we have collisions, we will actually have reduction of the path. So this will narrow our profile. And then actually this can be included in many different ways depending on how exactly the collisions happen. So we have simple Nelkin-Gatak, Galatry profile and Gilad-Bohr profiles. But then we have these two inhomogeneous and homogeneous broadening, so I should actually include it both. So I phenomenologically add these effects and then I get even more profiles. But really what you should do is you should just set up the correct equation, which is the generalized Waldman-Snyder equation, solve it, and purely ab initio figure out what are your line shapes. And so you can see that experimentally the problem is actually like ill-defined. It's very difficult to fit because we have this simple profile one-dimensional function. We have many different effects, and then we want to figure out from this what's going on, how these different contributions result in this. So the way we do this is we measure at many different pressures. You could fit many different profiles, but then if you're a beginning grad student without any support from theory, you might kind of think that it looks like trying to figure out dregs of tea leaves and coffee grounds inside the coffee cup. If you have some support from theory, then you can directly compare ab initio and phenomenological fit. And you can see that there's a bit of a problem because on one hand, the agreement is excellent, sub%. On the other hand, it's way worse than phenomenological fit. And well, why? Well, because theoretical and experimental frequencies of velocity changing collisions different by a factor of 2, which seems like a problem. So what exactly is this frequency? Well, it's basically the frequency at which the collisions that do not kill the coherence bring the velocity distribution back to equilibrium Maxwell-Boltzmann distribution. And if you do 2D spectroscopy of this system, like you will basically see this in real time. So you will decompose inhomogeneous and homogeneous broadening. You will measure spectra at different delays. And just by looking at how this profile, which is asymmetric, becomes this symmetric blob, you will just get directly this information on this time scale without having to interpret these very this linear spectra. So that's one idea for a measurement. Another idea is that, well, you have multiple dimensions. If you have multiple dimensions, then instead of this incredibly congested spectrum, you would be able to decompose it in more access and simply more easily see what's going on. So this is an example that I sometimes give that people have been trying to do breadth analysis with this linear spectroscopy. And the ideal way is to figure out concentrations and then based on concentrations figure out what's going on in patient's body. this didn't work because the spectra were too congested. So using brute force machine learning, somehow they managed to find out some predictors for patient health. But obviously we would prefer to figure out concentrations and have some physical model and biological model than just a black box prediction. And then, okay, so how do we actually do this? How do we do the experiment? Well, we use cavity-enhanced spectroscopy. So we have our cavity, we have cavity modes. It's very common to do this with CW laser. We essentially build up a standing wave pattern inside the cavity. And then depending on the finesse, we can, as Piotr Wcisło showed earlier today, we can go up to enhancement factors even of a few 100,000. So very much increasing our sensitivity. Or thinking about electric field, very much increasing the energy that is circulating inside the cavity. But we can also do the same with frequency comps. So what are frequency comps? So these are pulsed lasers, but they are very well stabilized in the sense that the delay between pulses emitted by the laser are very precise, and also the phase evolution from pulse to pulse is also very well stabilized. And in frequency domain, this corresponds to this comb of equidistant lines, which can be very narrow, the same way that you have with CW lasers. And that means that I can basically couple this comb of equidistant lines to the comb of cavity modes. And I can get the same kind of enhancement that people do with CW laser, CRDS, and cavity-enhanced spectroscopy, except in a broadband manner. So this is all very commonly done in linear spectroscopy by many different groups. And we can also do the same with ultra-fast nonlinear spectroscopy. So here we have the setup where we have linear spectroscopy. We have a single pulse circulating inside the cavity. And I can simply come in with the pump pulses earlier than the probe pulses, and they can prepare my sample. They can prepare some excited population that will then be probed by the second pulse circulating in a different cavity with the same focus, or in the same cavity, just time delayed. And this all works. I get a factor of proportional to finesse for pump power circulating inside, and I get the same factor for probe sensitivity. So in the end, I get finesse squared enhancement. And so what this allowed us to do already, back when I was a postdoc at Stony Brook University, is that we had this kind of setup and we used this to study salicylate aniline. So what happens in the system is that you go from ground electronic state to first excited state, and this hydrogen iter will jump here, and then the whole molecule will twist, or it will twist before it has the hydrogen has the opportunity to jump. So we either have this twist immediately, or we have this excited state intramolecular proton transfer, and afterwards it twists. And the question is, so what happens? So people have been trying to figure out what's going on for quite a while in many different systems. This is one of simpler systems where this kind of effect is thought to occur. So the way you study this is you do pump probe spectroscopy or transient absorption spectroscopy. So you have two pulses, you have delay between pulses, and then you measure the probe absorption, the absorption of the second pulse as a function of the delay. And the reason you do this is that, well, after you excite this molecule, then the spectrum changes. Changes in the spectrum will report on the dynamics that I just talked about. And you get this kind of spectra depending on delay. So you have some increased absorption, and then you have some decreased absorption. And then you do so-called global analysis, where essentially you try to feed the spectra with different decay constants to figure out different pathways of to figure out the kinetics of this dynamics. And what we have found is that we get very good agreement between our gas phase measurements and measurements done by Ziółek from Adam Mickiewicz University done 20 years ago in acetonitrile in the liquid phase. Here I'm showing also the decay constants for this kind of system where we excite and then the system goes down. So here I'm showing the curve for 420, 470 and 470, which does not agree so well, but the curve for 420 agrees. And the reason is simply because that when you're in a solvent, the whole spectrum shifts. So if you don't shift the whole spectrum, you're not really comparing what you should be comparing. But just for clarity, I'm showing all the curves, but if you compare the correct points in the spectrum, then you get pretty good agreement. And here we have something interesting, because here we have also gas phase measurements. So they should agree with our measurements, except they don't, because these are photoelectron spectroscopy measurements. And the problem here is that we're not comparing, for this kind of dynamics, if you're comparing optical absorption spectroscopy and photoelectron spectroscopy, you're not comparing apples to apples, you're comparing apples to oranges. Because if you do photoelectron spectroscopy, then the transition moment for ionization depends on the dynamics that you measure. So as the electronic state evolves, also the transition moment for photoelectron yield changes. And that means that the decay constants that you measure may be different than the actual decay constants of the electronic state. And this is basically what we see here, that from time result photoelectron spectroscopy, the decay constant is much, much lower than what we see in gas phase and in liquid phase. So in the end, also with simulations of exact times, of exact dynamics, you are able to isolate what happens. And essentially this part where it twists without transferring the proton, this situation does not occur. What we see is that we have the excited state proton transfer, there is decay through conical intersection, or also the molecule can get trapped in some long-lived state, and this is how you get photochromic glasses. So how do we actually do to DIR frequency comb spectroscopy? Well, this gets trickier than cavity-enhanced transient absorption spectroscopy, because what I want to do is I want to have 3 different combs in the same cavity, coupled to different transverse electric modes. So I need a delay line to generate different pulses that would allow me to also change the transverse patterns of these 3 pulses to match the transverse modes of the cavity. And I also need acousto-optic modulators to match the frequencies of the modes, to match the frequencies of my frequency combs to the modes of the laser. So in principle you can do this. And if you do this, then what you can see is that essentially you not only look at time dependence, the interaction of 3 different pulses with matter will also create a spatial pattern of excitation. So essentially the third order signal, the third order macroscopic polarization of the sample will be described by the product of the transverse electric modes of the profiles. So people also have been doing something similar before. You can think of it this way: you have 2 pump pulses, and they can create in this simple case, they can create a transient grating. And then the first pulse diffracts from this grating into different electric modes of the cavity. And you can calculate it precisely how well the signal couples with different modes of your cavity. And then, since we're in cavities, we also have to take care of phase matching, which means that our nonlinear signal will be generated at offset frequency simply given by the correct combination of the offset frequencies of incident combs. And this has to correspond to the round-trip phase difference. This corresponds to the round-trip phase signal in this cavity. And this has to match the Gouy phase of the transverse mode of the cavity that I also want to couple into. So I have to match these 2 things independently. And what is important here is that if all the signals that do not match all these criteria of phase matching and wave vector matching will be filtered by the cavity. Because as I said before, we have all kinds of nonlinear interactions. If we experimentally, it might be quite difficult to separate them unless you separate them spatially. But here I use the cavity to simply filter them out. Like the cavity will kill all the non-resonant signals by a factor of finesse squared because they don't match any of the cavity modes. So combining it all together, I also have another problem that if I couple light into cavity, all the frequency noise will be converted to amplitude noise. But then another trick is to simply first completely filter out the pump signals by single mode fiber to only look at the third order polarization, and to also do heterodyne detection and measure the signal far away from any kind of intensity noise. And combining this all together, we have working. We have part of the system is working. Large part is still in progress. Especially, we have a nice mid-infrared frequency comp source, but this has to be extended to generate the higher order modes, and also we need to build the cavity and the whole nonlinear delay stages. So with this, I would like to thank you for listening, and I wanted to advertise that there are opportunities for postdocs. Thank you.
Thank you. So now there is a time for questions, if you have any. No?
Well, I found it very interesting, the agreement you have in your experiments in the gas phase with the experiments in acetonitrile solutions. I would expect some difference, in the sense that I would expect some interaction of the acetonitrile solvent with the amino group of your molecule, but that is it. It's not a very. But I was wondering if you have tried other different solvents just to make this same studies.
So I know that people definitely have done some measurements with different solvents. We have also looked at. I'm not sure it's. I think it was also published some other molecules which have similar dynamics, and we also saw like the same. Roughly the same trend, that the dynamics are much closer, gas phase optical, liquid phase optical versus gas phase photoelectron. Which also, I think the common wisdom was that the gas phase should be closer to the gas phase, but apparently it's more important to compare apples to apples.
Nice. So thank you for the talk. So you mentioned that you could go up to finesses of 100,000.
Well, not for this.
Nah, not for this. Okay, but my question is still in that sense. You have to match the repetition rate of the comb very well, I guess, to the finesse of the laser. Otherwise, you have to the free spectral range of the laser. Otherwise, you have some walk off there. And I wondered if you could tell us a little bit about that, about how well that works, how much walk off do you have. And I guess you have an interplay with how precise you can be with the line width of the comb and the finesse in that sense.
Well, so it's interplay between the finesse, so the width of the cavity modes and the enhancement that we get, and the dispersion of the cavity mirrors, and the width of our incident radiation. Because you do the dispersion of the cavity, we have walk-off, as you said, between these things. So in my case, I plan to use cavities with finesse of around 1,000, not more. And in this case, looking at the mid-IR mirrors that you can get manufactured, you should get. I think it was around 100 or maybe even 200 inverse centimeters inside the cavity in the mid-infrared. So mostly like looking at the physics of multi-layer dielectric coatings, it's mostly the contrast between the two different substrates that you use. But it's doable to get nice enhancement. We even had, so it's more difficult in some ways in in the visible, but in the visible we were also able to get very, very nice behavior. I think I even should have because this was done in the visible, and the issue was really the same here, that we had this system that was working from 450 to 700 nanometers, and we were able to get to circulate pulses that had duration of 200, 300 femtoseconds inside the cavity, which had finesse of few hundred. So it's within experimental realm.
Okay, some other questions? Okay, yes, I wanted, because I think we have 1 minute. So because you said that the last point about polarization dependence, right, that you will not have time to say, but I mean, I don't know if 1 minute is enough to say something about that, or...
Well, the nice thing about molecules in the gas phase is that they rotate freely. And that means that you can think about, and you have multiple pulses. So that means that you can think about, well, what happens if I have these different pulses and I change polarizations of these pulses, and how it interacts with the rotational dynamics. Can I do some clever stuff with this degrees of freedom? So people have been doing this in the liquid phase, and they commonly use this so-called magic angle. But turns out when you consider what happens in the gas phase, then the dynamics are completely different, because you have free rotations, and in liquids you don't have free rotations. And since this is already past time, what I wanted to show is that basically you can, if you consider third order interaction, third order pathways, you can show that all the pathways, the polarization dependence is proportional to this kind of factor, which is a sum of 3 cosines. And if you decompose the complete response, you only have 7 distinct classes. And by manipulating the polarizations, you can kill parts of the response. So you can, let's go here. You can, for example, completely remove anti-diagonal part or diagonal part, or you can do the reverse. You can also, and we have basically shown experimentally that if you use specific polarizations, you can nicely, because you can nicely manipulate what you measure.
Okay.
Yes.
Okay, thank you very much.